begin.
Okay,
Not
thank
at work,
you.
anyway.
Not at work, no.
As I
Hello,
said,
Nigel.
audience participation is welcome, but John didn't say that.
It's welcome, but I also need to finish. So, okay. Okay. So Keith asked me, would I, some of the methods I've been talking about in sort of faster lectures, and of course in things like PowerPoint and LaTeX lectures, you tend to skate over the bumps. So what I'm going to do today is work my way through some Navier-Stokes results, actually on the blackboard line by line, to show people sort of the detail of how does one do things and how does one get certain results. So that's what I'm going to do. Now what I'm interested in, so 3D Navier-Stokes equation, standard notation. Sometimes I'll be doing unforced, sometimes I'll be doing forced. I've got a group of definitions here, which are in a way are fairly obvious, but what I'm particularly interested in is the phenomenon of intermittency. And in my talk last week, I went through some pictures and figures as to how intermittency looks if you put figures up. Now, particularly, intermittency in a vorticity field is a very spiky thing. So signals are extremely spiky. And if one looks at this definition, which I'm going to repeat, essentially, I'm going to, on my volume, I'm going to look at these objects, which are frequencies. I'm taking the volume out, I'm putting 1 over 2m, and so essentially this has the dimension of vorticity, so they're frequencies. They're integrated over the volume, they're functions of time, and their definitions are here for later on. Okay. Now, if you have a very spiky signal, m is 1, just the L2 norm, often washes over that. You simply don't see much effect from very sharp spikes. As you raise m very large, the higher m will actually pick up the spikiness of the signal. So this is the idea. I'm interested in finding results on these objects, time averages, this sort of thing, as much as I can, for large m, to see if we can actually see anything about intermittent effects in Navier-Stokes. Because I think it's important that experiments, numerics show that intermittency is a generic thing. It could be good if an analyst could show that intermittency comes up in the analysis. And that's what my task is.
N equals infinity.
And m equals infinity, of course, is the soup norm, and that would pick up the biggest spike. Okay, so frequencies, 1 over time.
You get the 1 over 2m.
Yes.
I've taken the volume out, I've taken 1 over 2 out. So they're all frequencies.
So the omega is less than 1.
Well, omega is just the vorticity, whatever it is, and I'm integrating over the whole volume of the space, which is a periodic box. Okay. Okay, so this is now what I'm going to do. Now, Navier-Stokes has a scaling. And if I take x, let me see now, x primed is epsilon x, t primed is epsilon squared t, p primed is epsilon squared p, etc., etc. Then Navier-Stokes is invariant, it's a standard undergraduate thing. So how do these scale under this scaling? Well, what you discover is that omega m to the alpha m scales like omega m primed to the alpha m, where alpha m is 2m over 4m minus 3. And this is for, of course, m greater than or equal to 1. And so this object here, which is written down here in pink, you can see it starts at 2 and goes down to a half. And it basically tells me to define that I'm going to use these, this is a definition, I'm going to use now, say, omega naught to the minus 1, and omega naught would be nu L to the minus 2, like so, and I'm going to put, okay, so this now has no dimensions, and I'm going to put it to the alpha m. And I'm going to use these dm's, which are now dimensionless and scaled with this. Okay, and they're here. Okay. And these are what I'm going to be working with. Now, just as a remark, essentially, if I look at this sequence of d1 is omega naught to the minus 1, omega 1, which is, of course, L to the minus 3 integral omega squared. That's d1. And then I go all the way across to d infinity, and that's omega naught to the minus 1, omega infinity to the half. Just as a passing remark, which I don't want to go into, if you look in the standard Navier-Stokes analysis textbooks, what you find is that the time integral of d1 squared is a well-known regularity criterion for Navier-Stokes. Come down to here, and the time integral of d infinity squared is none other than the time integral of omega infinity, which is the Biel-Kato-Maida criterion for Euler. And so basically this range of d's from d1 all the way up to d infinity is what I'm using. You're going from L2 all the way through to L infinity. And I want to try and get some sort of picture of how all these d's behave as a uniform set. Okay. Now what I'm going to do is very briefly take you through something you already know. Then I'm going to prove a result that the time integral of these dm's are actually bounded for weak solutions in Navier-Stokes. I'm going to discuss what that means in terms of the physics of length scales, etc. And then if I have time, I'm actually also going to look at an assumed critical lower bound on the time integral of these things that tells us hopefully something about intermittency and how it may behave as a relaxation oscillator. So that's where I'm going. Now, one of the other advantages of this, that numerically, people like Bob Kerr who have large data sets, these things are easy to compute numerically. They're a piece of cake. Many years ago, I used to be looking at gradients of the velocity field, and of course they're impossible to compute, and it took me a while to realize I was estimating things that nobody could ever calculate. But if you switch to these things, these are very easy to calculate from a data set, and that's one of the reasons I'm using them. Okay, so let's move on. Okay.
Could you give us some intuition about, for instance, if dm is large for smaller m, and
well, the alpha m. Well, I'm going to. Well, let me remark. Okay, since you ask here, let me remark. Okay, the omega m's, by definition, must always be ordered because that's Holder's inequality, based on that definition. So they always has to, they may stretch out or they may cluster, but they must always be ordered that way. But the alphas go the opposite way around. They go the opposite way, and therefore there is no ordering in the d's. So for instance, dm plus 1 might be greater than or it might be less than dm plus 1. And that's actually going to be critical because I have later on I'm going to write down a regularity criterion based on the relative sizes of these things. Okay.
but still, I mean,
Yeah.
What is the intuition? So for instance, you have large d1 and d2 and smaller d10. So
let me come to this.
Okay.
You're getting ahead of me. Okay. So let's let's do something simple. Let's look at, this is sort of what everybody does. Let's differentiate the energy, like so. And, okay, so what do we get? So we get the integral of u dot. Okay, so we have Laplacian u minus grad p minus u dot grad u plus, well, we'll leave the f off at the moment. Well, no, we'll put it in. Plus f dv. Okay, so what does that give me? Well, these are easy to do, and so is this. Here we have minus nu, the integral grad u squared. Here we have minus u dot grad of a half u squared plus p plus the integral of u dot f. Okay. Now, as all good undergraduates know, u dot grad phi is div of u phi, which disappears because of periodic boundaries, plus phi dot phi times div u, which is 0 because we're an incompressible flow. So this has disappeared. Okay, this thing in L2 on periodic boundaries for divergence-free fields is none other than omega squared. Okay, and this thing we can break up and write that by Holder's inequality, a half and a half. Okay, so now we've got something reasonable. Okay, now, yes, because I'm doing it on that.
This is not Cauchy inequality?
Yes, it is. Yes, indeed. Okay, now, here we come to something. Navier-Stokes analysts, you look in all the classical textbooks like Ladygin-Skaya, Timam, Constant Fouriash, they always have this body forcing, which is highly unphysical, but that's simply the way they do it. And they define the Grashof number based on the L2. So as long as f is a bounded L2 function, you have this thing called a Grashof number. So this thing is like the Grashof number. Here. Excuse me. Here it is, excuse me. I think this is designated for one's pocket, actually. Okay, there we go. So, now what I'm going to do, I'm going to time average up to some time t, which is simply 1 over t, the integral of f. Okay. Yeah, that's right. So I'm going to time average, and what that gives me is nu in time average integral omega squared dv, and I think we will all recognize this, what this is less than, okay, now this stays outside. I can write that Cauchy, okay, and then you've got a term which would be like order t to the minus 1 based on the initial conditions of the energy. Okay, so what is this? Well, if I put an L to the minus 3 on this, well, you would all recognize that as the energy dissipation rate, like so. Okay. Now, what does this look like? Well, if we rescale this, this is like G, and if Grashof, and if we rescale that, this is like Reynolds number, like so. And this is your energy dissipation rate. And so what do we end up with? Well, if I readjust these coefficients for this omega naught, and of course you recognize this as D1 because alpha 1 is 2, what you actually find now is that readjusting the coefficients is less than Grashof times Reynolds, like so.
Something I missed in between the lines is you've made an assumption that d by dt of u squared is
zero or less
No.
than something?
No,
Your average is zero.
no.
You have a less than or equal sign.
Yeah, but
d
I've got something positive minus the initial conditions which can go over there,
Right,
and the
okay,
left,
so that's
and,
what happens.
and I've integrated
That-
and
that
I've
goes in
lost.
order t minus
I've
one.
lost the integral of u squared
Right.
because it's positive. But I've ended up with this thing, like so. Okay, now it's mixed in Grashoff and Reynolds, but every good numerical person and experimentalists would much prefer the Reynolds number, and they don't like, obviously this is a wholly unphysical object. But then in 2002, Dorian and Foyash in JFM did a very neat calculation that showed that for Navier-Stokes solutions, the Grashoff number is actually less than some constant times the Reynolds number, which is a very neat result, extremely neat. And so you can essentially say that that's some constant times Reynolds cubed. Okay. And this is a result we all know and love, because essentially it's saying that the energy dissipation rate is bounded above by Reynolds cube. Now, how do we define the Kolmogorov length? We would define the Kolmogorov length to be like, well, it's like lambda k to the minus 4 is like epsilon over mu cubed, like so. So if I retranslate this, what I find is that that's Reynolds to the 3/4, like so, which is a result that we all know. And of course, it's not come from Kolmogorov statistical theory, although it gives the upper bound gives you the same result. So it's very nice that the analysis fits together with the statistical theory, but it isn't dependent upon it.
But viscosity coming into the GR and RE, but when you went from the,
Yes.
so you replaced the F2.
Well,
by
it's
the-
here, but you see omega naught, which is in minus 1, which is in this definition here, it's in there.
Oh, okay.
So I haven't done every little line of the algebra from there to there. It's just a simply a little bit of algebra. So I've done this to basically show you that if you do these methods, it gives you a result that we all know and love.
Well,
Okay.
we really all know it.
Sorry?
I don't know that we all know it. We may love it without knowing it. But
Well,
but-
the Reynolds to the 3/4.
Yeah, but I know it in the sense
Yeah.
the lambda k to the minus 1
Yeah.
is of order.
Yes, and this is less than or equal to. So you could have flows which are actually less than this.
You mean on large? Well,
Well,
the way the inequality goes is puzzling me. I mean less than.
yes,
That means the lambda k could be greater.
Could
the
be
length
big-
scale
yes,
could be great. The length
Yes.
scale on viscous dissipation could be greater
yes, yes,
than the Kolmogorov scale.
yes.
Well, it could be less.
It
You're saying can't be less.
Well, remember, all this is just based on that definition. The whole point of what I'm doing, I'm now going to go up to actually higher values of 2 and
Yeah.
see what we get.
Yeah. Oh yes, of course.
Yes. You see, this is the whole point. You can have very fine scale stuff in your signals, and the L2 norm just misses it. Okay.
So what it's saying, when I do a calculation, is
Yeah.
that if I do it to the order of magnitude of the Kolmogorov scale,
Yeah.
the turbines might be larger scale than that, but that's as much as I absolutely need to do the calculation, refine the small scales
Well,
properly. I'm interpreting it in terms of my numerics.
let's come to that afterwards.
Right, you have to look
Okay.
at the higher order ones. and see-
Okay, now this I've washed over it all. This doesn't guarantee you. Now, if you're going to be a strict analyst, this doesn't guarantee you a strong solution of Navier-Stokes. In fact, it doesn't. You go back to Leray in 1934, and essentially this is a weak solution result. And weak solutions are essentially they're things that you can't essentially write down. They only have any meaning if you integrate them against a test function. And they operate very nicely in L2 because they're basically based on you project your solution onto a Galerkin set. And projection operators operate very nicely in L2 because you take 1/2 and you have a projection and you can lift the projection over and they all behave nicely. The problem is I now want to go up to higher LPs. And then with the method that Leray used, you've got a problem. And so I really would like a similar result for DM. And of course now you're in higher LP norms. So you can't do it the way that Leray did it. Okay, but there is a way around this. And so I'm going to state my result, which I will write as a theorem, and let's say that says weak solutions of 3D Navier-Stokes obey, and in fact it's like the same result, dm okay, up to time t, say up to time t, is less than or equal to some constant. It's still Reynolds cubed. Okay, so how did I achieve that? Very, very crudely and very quickly, because now we're in higher LPs. Well, this whole business revolves around the result of Foyash-Guillaupe and Tamam, 1981, which is very little known. It was like one of the very early volumes in communications in PDEs, and at that time it wasn't a well-known journal, and the results sort of got forgotten about. And I spent some years advertising it. And what they proved was the following. They proved that the time average you now take, and you'll see why I'm doing this, now go to these H's, n derivatives in the generalized sense of the velocity field in L2. So H naught is just your energy, H1 is your entropy, but I want to go to higher derivatives. They prove this result, and you don't need to see why. It's true. It would be nice to have the time average of the Hn. Now, it's some constant which is which has dimensions, and I can't remember what it is. And if we use Doring and Foyash, we can translate that to Reynolds cubed. And this result you can actually prove for weak solutions of Navier-Stokes. It's rather remarkable that it's true, but you can. And then, having used their result, I'm going to adapt my DMs, and you'll see why. Okay. Now, I'm going to take my vorticity field in L2M, which in effect, forgetting about all these coefficients, okay, is in effect omega 1. Okay. And I'm going to say, right, that, now if you'll forgive me, I'm going to do one, this is the only Sobolev inequality in the whole lecture. Okay, I'll go up to n minus 1 derivatives of omega in L2. Now that's n derivatives on the velocity field, so that's exactly my Hn here. Okay, and the way these things work, you calculate some number. So what you're doing, you're interpolating, you're bounding between a higher LP and a lower one, and if you want to do that, you've got to invoke some derivatives to do it. So all the Sobolev inequalities are. You're going from a higher to a lower. You can't have a constant there. You have to have some derivatives. This I won't give you, but you calculate it by dimensional analysis. I want to time average that. How high can I go is the question. How high can I go in terms of a power? So I'll do that.
Is m on the right-hand side, or is it another?
No, it's the same m. It's exactly the same
No, I'm
m.
saying it's the gradient of n minus 1 should be that gradient m minus 1.
It's n, no, that's n. that's the chalk, that's n. Okay, so for some n
Okay.
greater than or equal to 3. Okay, so I'm going to put that to the an, and I'm going to time average. Okay, then I'm going to break this up by Holder's inequality. And when I break it up, and I won't do the detail, but when I break it up by Holder's inequality, what I discover is that it comes out to some C, it comes out to some D, whatever they are, it doesn't matter, and I can only do that, and of course this is exactly the result here, I can only do that if the AMs, and that when you actually work it through, the AMs have to equal 2m over 4m minus 3. And that's exactly my alpha m. So the whole process only works if, when I say I want to have as high a power as possible, the more the exponent, the more regularity you have. So I want to get it up as high as I can. And when you work it through, the only AM that fits is exactly alpha m. And so this is exactly, and this is bounded, and that's bounded. So I'm in good shape.
The H's have omega or U in them.
Well, grad U in L2 is exactly the same as omega in L2. So n minus 1 derivatives on omega is n derivatives on U. That's the HN. Okay? And so dimensionally, it turns out...
Is this for arbitrary C and D, or is it?
No, these,
No,
these...
the exponents, do they have to equal sum to A sub m or something like that?
No, you just do this, and if you're wanting to have that here, and you want that there, there is only one answer you can have. You just work, it's only algebra, and you work it through, and you find the only way I can do that and do a Holder inequality is that the AMs become these alpha m's.
No, I'm saying is the C and D, are they just for all C and Ds?
No, I'm not giving you all the detail. I'm just doing a Holder inequality.
C,
And you
is
get
equal to B times A sub m.
Yeah,
B is equal to
sort
1
of.
minus B.
sort of, yes.
Yes, okay, fine.
Yeah. And so the AMs are actually come out to be the alpha m's. And that's exactly why, that's where my DM comes from here. Okay. Now I'm not going to keep this proof. And so we've circumvented this problem. We've circumvented this problem that you would normally have in dealing with higher LPs. And so now, this allows me, now since basically said, well, D1, we go to here, actually what you find is that when you define the length scale, which I'll call lambda 1 to the minus, if we say dm is defined to be lambda m to the minus 1 to the 2 to the 2 alpha m, as you say, jinxed. Right? Yes. If we make this as a definition, alpha 1 is 2. So when alpha 1 is 2, there's the fourth power for the Kolmogorov length. So it gives me a quarter. I'm making this as my definition for a set of length scales. And so when I do that, I get from here 3 Reynolds to the 3 over 2 alpha m, like so. And so alpha 1 being 2, there is the 3/4 for like the Kolmogorov length. And now, Keith, I think this answers your question because, of course, as m increases, alpha 1 goes down. And so this estimate goes up. And so it's allowing, you're picking up smaller and smaller scales. Yeah. And in fact, alpha infinity is a half, and so that's Reynolds cubed. And you're probably down onto molecular scales by then. So but basically you've got a continuum of length scales from Kolmogorov all the way down, probably to where Navier-Stokes fails as a model. Now you do have to ask yourself the question, weak solutions, they're proven to exist, but they're not unique. And so you have to ask the question, does a resolution length scale have any meaning if your solution is not unique? I don't have an answer to that. I'm just putting it out there as a query. Okay, but this, as far as I can see, using these methods, is the best one can do, well, the best I can do, in trying to pick up some idea of a length scale based upon these objects here. Okay, so now let's move on. Okay, so in fact what I'm going to do is put that in here. Lambda m to the minus 1 is basically less than Reynolds to the 2 alpha m. Okay. Now, what about the evolution of omega m or dm in time? Can I say anything about that? Okay, well it would be nice actually to get a differential inequality for the omegas or the d's themselves. Now you then run into a problem. Many applied mathematicians of the British school don't care about these things, but analysts do. The problem is this, you only have weak solutions. You're not legally allowed to differentiate these objects with respect to time pointwise. It's a sort of an illegal act as far as mathematics is concerned. But there is a way out, and the trick is this. Time derivative. Differentiate with respect to time. Okay. So the trick is this. This is the way analysts get out of things. You assume, what you do is you assume a maximal interval of existence and uniqueness. And you call that naught T star, say. Okay, and it's going to be a contradiction argument. And the contradiction argument goes like this. You assume there's a maximal interval of existence and uniqueness. Now, if the interval finishes there, then it tells you that the H1 norm, which is in effect omega 1, at T star must be infinity. Because one of these well-known facts in Navier-Stokes that if the H1 norm is bounded, everything's bounded. It controls everything. It's the point guy that controls everything. Okay, now if this is maximal and it finishes there before T star, then omega 1 at T star must be infinity. Okay, now having assumed a maximal interval of existence and uniqueness, you can go ahead and do anything you like on that interval, quite legally, but then when you've done it, you then have to take the limit of what you have as t goes to T star. And if in your limit it's finite, you have a contradiction because this must be infinity. Okay, that means that if you've achieved that, then essentially your contradiction will say, well, the interval is not maximal. So it must either be 0 or infinity. It can't be 0 because there's always a little interval at the beginning, so it would have to be infinity. That's the strategy, and it's well known in geometric analysis. So it's a trick to get out of jail, and then you just go ahead on this interval and do what you like.
And in fact, you're assuming there exists regular solution, not
yes,
weak
strong solution,
yes.
Existence and uniqueness, so they're strong solution. So now we can use that, and we can go ahead and in effect do what we like. Okay, now I'm going to do one calculation. Let's, just to show you the flavour. Okay, now what is that? That's none other than 2m. That's d by dt. This is my definition of omega to the 2m. Okay, and that's none other than, well, we'll come back to that. So let's do that. So that equals the integral of 2m times the integral. It actually comes out to be this, u dot grad of omega to the 2m dv plus 2m, and then what you're going to have is omega to the 2 into m minus 1 omega dot grad u. So there is my vortex stretching term. And here is my u dot grad omega. Now, of course, in the time-honoured way, this disappears, and this leaves me with this thing. And that is, the 2 and the 2 there become omega to the 2m grad u, like so, with a 2m. Okay, so I'm going to break this up, and you'll see why I'm doing this in a moment. Okay, now this thing is 2m L cubed omega m dot omega m to the 2m minus 1. And that I'm going to break up in the following way. Integral. I'm going to take one of these m's and write it as 2 into m plus 1, m over m plus 1 times 2. Okay. I'm going to take another of these m's and write it as integral to the 2m to the half. So this is Holder's inequality, multiplied by, and I've got the grad u. Grad u to the 2 into m plus 1. Okay. Now, do these add up to 1? Well, they do. You can see m plus 1, okay, cancels, giving me a half, and a half is 1. So that's Holder's inequality. And that's the trick of basically breaking that into 3 parts and having 3 Holder exponents, like so. Now, why have I done that? Well, the answer is that if I put an L cubed and then an L to the minus 3, an L to the minus 3, and an L to the minus 3, this is none other than omega m plus 1 to the m. This is omega m to the m. So that's this one and this one. And this thing, there is one more inequality. It turns out that grad u is less than omega, an LP, with a constant, provided p is greater than 1, but it is not infinity. That was one of your questions, Keith, earlier. And strictly, you're not allowed to have infinity there because grad u in L infinity needs higher gradients. It needs, it's basically the Beal-Kato-Maida inequality. You need a log of one of these h's, h3, at infinity. But as long as p is finite, you're okay. You don't need the logarithm. Okay, so I can replace that by omega, and I have another omega m plus 1 to the 1, so that's plus 1. And now I need a cm in there. Okay, so now let's piece all these together. That goes, I can move those underneath, and it tells me that omega m dot is none other than Cm omega m plus 1 over omega m to the m plus 1 times omega m squared. Okay. Okay. Yes. Right. And so what do I have? I have this thing. So now I've got now this is just for the this is just for the vortex stretching term. I haven't put the Laplacian in yet, but it's sort of looking promising in the sense that I've now got ratios of these things acting against one another. So I'm just going to give you the answer, and and the answer with viscosity in is the following. You take one of these omega m's out, you get this thing, and I put an omega naught to the minus 1 there. Omega naught, yes. I put okay, so what do I have? What do I have from the Laplacian term? Well, the answer is, and I'm just giving you the answer, is that you get exactly another constant, m plus 1 over m to some power beta m. And this beta m is 4/3 m into m plus 1. So it's quadratic in m. And so now what you have...
Is that just a rewriting of the line above then?
Well, that's only the vortex stretching. This part is rewriting of the line above. This bit is now the Laplacian, which I'm not calculated, I'm just giving you the answer.
What I don't see is just where this second last equation...
This, omega m squared, this over that, is exactly this thing. This was just for the vortex stretching term.
Oh, I see,
It's
this
on the
other
left-hand
term.
side,
Yeah.
halfway
Where's
down.
the other term?
Just for the vortex stretching term only.
I've lost something.
No, this is that. That's the vortex stretching
Yeah.
term. I've now done the Laplacian, and I haven't done the working, and I'm giving you the answer, and the answer is,
the viscous term, you mean?
Yes.
Yeah, I see.
and the viscous term gives you that. I'm just telling you the answer, because it's too long.
So the omega m dot is less than.
So it's less than something negative and something positive. And these two ratios are basically competing against one another. Now, if I put m is 1, this is the ratio of, in effect, the fourth order moment to the second order moment squared of the vorticity. And that's actually the flatness of the signal. And as I said in my lecture last week, flatnesses in turbulence can get up to like 6 in the wind tunnel, 12 in the financial markets, 40 something in the atmospheric boundary layer. But basically this is a generalization of the flatness of your signal. So you're expecting in turbulent flows for this guy to be really quite big. The question is, though, that we can't quite nail how big this is going to be versus that. Specifically in terms of analysis, we can just say, well, there's clearly a competition between the two. So the question is, what can we do with it? Okay, what can we do with it? Well, I can peel these two apart. I can use Holder's inequality. It's a trivial back of the envelope calculation. And by Holder, I can make this into that, peel them apart, and I'll just give you the answer. And the answer is that you get omega naught to the minus 1 omega m, and lo and behold, you get 2 alpha m, the famous alpha m. That's exact. And of course, by by doing this, you're basically changing your constants in so doing. And so basically now you've got a competition between the generalized flatness and none other than dm squared, exactly my dm. And so if I translate all this well, I failed in one of the aims of this seminar. I was hoping to do the whole thing in 2 blackboards. But if I translate this into d's, it's easily done. It's just trivial. Okay, and then that becomes dm cubed. You see, that will give me a dm. That's dm squared. I've basically got, I get a constant which I call omega 2m, okay, and then I get and this rho m is just now 2/3 m into 4m plus 1. Okay, and these are just constants with the omega naughts in them.
So your term above that with the 2 alpha m,
Yeah, that's
that replaced the ratio of omega sub m?
well, I had an omega m times something times one of these to some different power. I just peeled it apart using Holder. And took
So
one,
you have- but
hang on,
you've
and took
taken
one,
an omega m out in front of that already.
well, that was already out, yes.
Oh, so there was an omega m there, but inside.
There was another omega m. It's omega m squared,
Ah, okay. I
omega
see.
m, another omega m
Yeah.
times one of these. I
Right.
peel the whole thing apart
Right, okay.
and combine one half with this. It leaves that as the other part. It's
Right.
just Holder's
I know, I
inequality.
just wanted to make sure I'd written it down.
Now this becomes dm squared. That gives me another dm, so there's the cube. And when I translate those into these, essentially, I have another dm cube, which comes outside. That's just algebra. Because remember the scaling on these, this has a 1 over alpha m plus 1, this has a 1 over alpha m. Okay. So,
We're going to change it from notation here. Omega 1 comma m and
oh,
omega
these are omega 1m is none other than omega 0 over c1 m, and omega 2m is omega 0 over c2m, and that's actually 1 over c1m. So 1 over, and that's C2m, to be more specific. Now, what this tells you is that I can get my dm dot to be less than something negative, provided, in effect, dm plus 1 is greater than dm. The combination of the constants is the triviality. So there is a numerical test there. These d's are easy to compute, as Bob has found. They're trivial.
What's omega not with a
That's
overline? No, that's without an overline.
yeah, the overbar.
oh no, sorry.
Okay.
Just, yeah. So there is a numerical test there. Are the m plus 1s greater than the m's? Because as I've said, although omega m plus 1, they have to be in the sequence, the d's don't. And so I said to Bob, can you take your data and can you run out these guys and let's see what they look like? And I was confident that, you know, most reasonable Navier-Stokes flows from reasonable initial conditions would definitely show that they order themselves with the lowest at the bottom increasing. And when Bob's data came out, it came the other way round. That the highest is always lower. So it's the lowest at the top going down. So in other words, those codes are running essentially in a region where this is less than 1, not greater than 1. It doesn't invalidate the theorem, it just says... Now what this says is that if that is greater than this is always decaying. And of course, for many initial conditions, it isn't always decaying. It might be jumping around.
Wait a minute, if it's less than 1, and you're raising it to a large power, rho n, so it's very small.
Yes.
So that's the viscous term.
That's the viscous term.
Which is small.
Which could be small, and therefore dm dot is less than something positive times dm cubed, and therefore you don't have anything. Dm dot could be positive or it could be negative.
So what would happen then in the other sense if it were ordered the way you wanted it?
Well, if this was greater than that bracket would be negative.
Yes.
And then dm dot would be less than minus dm cubed,
Yes.
and dm would always have to decay.
Yes.
And
Right, you're wanting to prove.
And if the dm's decay, so do the omega m's. And any omega
And
in
you
L,
have regularity.
and you have regularity.
I see,
Exactly.
you're trying to prove a singularity.
No, exactly the other way round. Yes, exactly the other way round. So basically, now Bob, I say, ran this out, and it came out the other way from which I hoped. And so we asked Diego Donzis, who looks after the Texas data set of 4096 cubed, would he run the same thing through? He got the same result, as did Rahul Pandit in Bangalore on his code. So they're all consistent. They seem to all be operating where in effect dm plus 1 is less than dm. And I actually have copied some graphs if you want to see them afterwards. Okay. So it doesn't mean this theorem is invalid, it's just basically saying that these numerical calculations are operating in a region outside of where this would predict decay on the Ds.
Can I ask you
Yeah.
about the equation which is in the red box over there?
Yeah.
So we know that omega m plus 1 is greater than omega m.
Yes. Yeah.
Okay. So it means that essentially, so that the bracket is greater than 1. So even if it is 1, then you have the equation which is that evolution is bounded above by the quadratic function, which actually leads to a blow-up, right? I mean, it could
Well-
essentially just tell us
Well,
nothing. So to say.
even if this was 1, you could actually, which you can't guarantee it will always
Then
stay
there is
1,
nothing.
because this is greater than and that's less than.
Exactly.
Yeah.
So essentially it could just blow up in finite
It could,
time.
indeed.
So the message is that once you take the corresponding power here, then
Yeah.
for dm you have a much better situation.
Yes.
So
So
it's-
now I've put in the viscosity here. So I've got that plus the viscosity with this minus sign, and now I've got this competition between the two, which comes out as this competition in effect between the Ds. Now the advantage of this, as I say, is that Ds are easily computable from data, very, very easily computable. Now how much time do I have, Keith?
5 minutes.
Okay, well, okay. Then I'm going to have to shift 5 minutes. Right. Now I'm just going to briefly, extremely briefly, summarize the result . I can do better. I can actually do better than just look at this point-wise in comparison. I won't write it down, but I have a theorem where I have a time integral of a log of one of these things, and that's a much weaker result. And as long as that time integral is positive, then the dm's decay. But nevertheless, in the runoff data, there is no region anywhere where dm plus 1 is greater than dm. So my theorem is true, but it and the numerics are doing different things. Okay, I'll skip over that. Now, my second result on intermittency. Okay, and this is very brief. Let's take a look at this time average. That's true. Okay. Now, if I integrate this result a different way, and with 4 minutes to go, I can't give you the details. Essentially, I can integrate this to look like the following. And it's a simple integration, exponential of minus twice It's a piece of undergraduate differential equations if I actually showed you what this was. Okay, it's a trivia. And what are these x's? Well, these x's are the integrals of these x's are nothing more than, now they come out to be something, and I can prove they're bounded below by the integrals of dm. Just give me a moment, Bob. I've only got a moment to go. Yeah. Okay. This is just with a little bit of help from Holder, and this is our first year undergraduate integration of a differential equation.
So it's the dm squared is less than or equal to exponential dot, and that's...
Yeah, no, the whole thing. It's the whole thing. The whole ratio.
Divided by
they're
the
divided by, this is less than the whole thing. Okay. Now, take a look at this. This thing, I know, is bounded above. This is the energy dissipation rate. That's bounded above by Reynolds cubed. I don't have a lower bound on that. I have an upper bound. And this is greater than. So what I'm going to do is put in like an assumption, one of many regularity assumptions. And I'm going to say, assume that in effect, this behaves like 3 into 1. Let me see. What was it? Sorry, not 3 into 1, 3 delta m, where delta m is some number that lies between 0 and 1. So I've got some slack in there. The question is, does this give me anything? Because now, I can now put this as Reynolds, the 3 delta m multiplied by this rho m gamma m plus 2. And I can now divide this into this. Does that give me anything? Well, the answer is, it does. I can make sure that that term is smaller than that term, so the minor, you're not hitting a singularity, okay? I want this to be big enough such that the exponential collapse is so quick and so fast that this term is always smaller than that term. And the answer is, in effect, the following result, that, as I finish, that for large initial data, and that's important in Navier-Stokes because small initial data is no good. And I could give you what this delta m is, but it's basically less than between 1 and 4. Then, with that assumption, it's
1 less than or equal to
4.
4. Thank you. 4. With that assumption, essentially, then the dm decay, and you've got regularity, and this delta m is some very complicated, yes, delta m is less than 1 and greater than. And this gamma m is just some function which you can work out. So I have enough slack in there I have enough slack of choice of this delta m such that if I impose this lower bound here, I can essentially make sure this is always positive. Yes?
Actually, for the GM squared, do you mean to have two time integrals in the denominator?
Yes. The integral of the exponential of the integral. I can handle it. It's okay. Fortunately.
What is the definition of xn?
Well, I haven't had time to give it. If I gave it and I did this integral, I did a Holder inequality, it simply comes out to be this. I can show you. It's easily done. Okay. And essentially that's saying, therefore, that provided this time average or this time integral holds above critical, then Navier-Stokes regularizes itself. But just to finish, of course, it won't stay above critical forever. It's not natural for Navier-Stokes because it will be exponential collapse. It's not natural to start from some initial condition, collapse exponentially and stay there. Okay, so I think basically what's actually happening is that if you start sufficiently large initial conditions, you get exponential collapse. Okay, and then essentially what happens is the dm then collapses exponentially, and then the average starts to go down because of course you've got a very short tail and the average, you've got nothing contributing to it. So finally the average drops, and the average drops below my critical value. I've lost my constraint, and essentially then I get growth again. Then you have another delay while the average starts to increase. It takes a time to increase. It finally goes back up through critical again. Goes up through critical, it collapses again. So essentially you have this spike, a collapse, a delay, a growth into a spike. This is being forced, thank you.
But
You
it's,
had forcing.
Well, I didn't.
and I don't think, if you look at my results, I don't think the forcing is critical.
The forcing is not critical for this.
The analysis is critical.
For this problem, the forcing is not critical. This is much easier to do for decaying. Thank you, Steve, for pointing that out. In this case, it is forced. And like I say, so essentially what you get are these spikes with delays in them as this average drops below and then increases above, it goes down and then it goes up and it goes down. So it's like a relaxation oscillator. And this essentially comes through this lower bound idea. But there is a gap where as it drops below the lower bound, you could still have singular behavior in the Ds. Because it's perfectly possible, and I will finish after this, it's perfectly possible that the Ds could become very large if they contributed, like in a spike, if they contribute enough to push it through its lower bound, then it's not dangerous. But it's perfectly possible to have growth in a D where it contributes very little to the time average. It doesn't push it above the bound, and those are the dangerous regions. So there is this gap where you could still have singular behavior. So I haven't solved the regularity problem.
Average at D sub m is that it could drop below that,
Yes.
and then it can then go above it, but
Yes.
then you're getting a much higher D sub m. So there's a short period of time where it goes way above it. So there isn't a strict.
But integrals have histories in them, and so they
Yes.
take time to catch up.
Right.
So if the DMs collapse exponentially, it takes time for the average to drop.
Right.
And that's why you have a sort of delay. And then when it's finally dropped below critical, and the DMs pointwise start to grow, again, they take time for the average to catch up and start to grow. So there's always a set of delays in between the spikes, and that's exactly what intermittency is. And so this is my picture of how sort of intermittent spikes come out of this analysis. And I think I'm done there. Thank you.
That's a wonderful exposition, nearly all on two blackboards. Thank you. And I think you're a long way towards that clay million for this Just a bit more, maybe 700,000. I wonder, I mean, this result, that dm plus 1 is always greater than dm for all m pretty well. It should be possible to either prove it analytically. Can you prove it?
No, I can't. You
And that's
can-
a challenge, isn't it?
This,
Yeah,
you
I see
see,
that.
these are the lows, and it's the higher that's coming down, and they all lie beautifully below one another. There's
Well,
no
we should-
crossover.
We should be trying to prove it analytically.
Yeah.
It's amazing that
Well,
it
it's
comes
not
out
only
of
is
the
it
competitions.
true of Navier-Stokes,
Well,
it's true of Euler after.
Sorry, what is it?
It's
It's
true of
Euler.
Euler,
Okay,
in addition, after a little period of time.
yes.
no,
Oh,
but Keith's
you mean
point
you
is
can-
right.
You can start, you can fabricate a field for which it's non-zero. It goes the other way.
For Euler,
For
they
Euler,
cross over
yes,
for
that,
Euler.
that you can fabricate a
But
field
not for
that will do that,
Navier-Stokes.
but
Yes.
will almost immediately cross over to that.
Yes.
For any sign of anything that's
So I
growing
think we need
fast.
to understand what it is in the dynamics that
Yeah.
causes that.
It's
Yeah.
a very, I cannot see anywhere, and I've worked in Navier-Stokes analysis 25 years, any hint that dm should always be less than or greater than dm plus 1. It may be a result that's true that we don't know about, or you may, if you pump the Reynolds number up very high, it may be that you might get a crossover at high Reynolds numbers, and we're just not near the regime. But it is intriguing.
Interesting.
There's no reason why the initial condition should satisfy for any equation.
That's right.
So it
I'm sorry?
seems-
There's no reason why the initial condition, whichever equation you
Yeah.
solve, should satisfy this ordering of the d's.
Yes, because
I agree.
yes, they must, because they're integrals over volumes,
Yeah.
and so this is Holder's inequality.
Oh,
On the omega, on the omegas. I'm sorry, John. The omegas have for all initial conditions, but the D's no.
Yes.
Yeah.
But you're claiming that after a while the D's are ordered in the way.
Yes.
you hope.
Yes, indeed.
So it's something in the dynamics that does it.
There's something in the
And
dynamics that
that's
does it.
worth exploring.
And that, my argument is these D's are important because they're defined through the symmetry scaling of Navier-Stokes. The alphas come out of the invariance scaling, and that's why they're the natural variables,
Yeah.
is what I would argue.
Yeah. No, it's very nice. That's a
Yeah.
great challenge, I think.
It's a little bit as the same question.
Yeah,
that I
yeah.
had before. So could you give an example of functions or of fields with high D1, D2 and lower?
I haven't been able to, it's a very good question. I haven't been able to do it yet. I've not been able yet to sort of construct. I ought to,
Yeah, one could come
I ought to
to
sit
these
down
things
and
very
try.
simply, almost analytically, for fabricated velocity fields
Yeah.
consisting of just one or two Fourier
Yeah,
components.
yeah.
See what it looks like.
Maybe that's what I should be doing on this day here.
Yes. Good idea. Periodic something to do.
Yeah.
John, what do you expect in 2 dimensions about the ordering?
Well, the ordering, by definition, it's got nothing to do with the dimension, but whether, it's a good question. The answer is I don't know.
You don't know.
I don't know, because of course 2D is a wholly different animal
Ah.
than 3D.
But you're saying that the Dorian-Fourier result doesn't apply? in
Oh yes, it does. The
Oh, it does.
Dorian-Fourier result actually is true in any dimension. It doesn't.
Grashoff times Reynolds.
Yeah. Oh no, I'm sorry. No, that is no. The Dorian-Fourier thing is this,
And that's true in any.
and that's true in any dimension. Yes.
But then
Reynolds
what
number
about
larger.
your box? Is that?
It's not that.
Well, larger than something very small. It doesn't have to be.
Yeah, but it's bigger than the Reynolds number, less than something like the Reynolds number squared.
Yes, no, I'm replacing this with this. Actually, they proved also that the energy, a time average energy dissipation rate is bounded below by G.
Yes.
So basically, yes, your Reynolds would have to be bigger than 1 or something.
Yes.
Yes, being greater than G, it's a very interesting result. Nobody's ever really exploited that. It actually has to be big enough.
Yeah, Conrad.
Can any of this be adapted to scalar transport? Field of gradients of a scalar?
I think it's possible that it could, yes. I haven't tried. I've been locked in wrestling with this.
Gradient and scalar, yes.
Yeah, it is certainly possible. But I think one just needs to be guided by the symmetries of the problems, that you choose the right variables that the system tells you to use.
The same, of course, magnetic field in dynamo. We're usually only concerned with establishing exponential growth. But I suppose the problem does arise. Can the magnetic field become singular, like vorticity? I mean, is that an open question? Or infinite time, maybe? I wonder.
I mean, you could generate small scales which then disappear because of and then you build them up again. In that sense,
Yeah.
there's a similarity to what,
Yes.
what John was
There is an equivalent to Biocado-Mito, and the paper, Brandenburg and myself, and the subsequent work by Grower Marigliani has addressed that issue from a numerical point of view.
Yes.
Yeah, it was Keflis, Clapper and Steele proved that you adapt Biocado-Mito from the integral of omega infinity plus j infinity.
Yes.
And if that's under control, then there's no singularity in
Yeah.
ideal
But
MHD.
the magnetic energy, I mean, which L2 normal magnetic field, let's see. Of course, if you've got forcing everything.
But j infinity bounded is a very stringent, is a pretty stringent
that's
control.
Yes.
But that's the natural result that comes out.
J current.
Yes.
Oh, yeah, I see.
Yeah, omega infinity plus j infinity.
Sounds very unrealistic.
If you take the analog of Euler, it's ideal MH, well, magnetic energy, well, you've got an energy constraint. Constraints on magnetic energy, which you don't have on entropy.
Yeah.
So there's a big difference. John?
The vortex stretching term, which was in the middle of some board,
Yeah.
you just took big, I can't quite see exactly where you did it. You took very big bounds on the velocity gradient. You threw away any subtlety about the orientation of the stretching.
I think, are you meaning in here? I had an integral of grad u.
You had omega dot omega, grad
Yes.
u dot omega.
Yeah.
Yes, top line.
It's on your left-hand side of the board still.
So do we have any,
Yes, here, this.
so you just took
Yes.
big
Here.
bounds on everything?
So I basically wrote that as less than omega to the 2m
And
mod
the velocity
grad un. So I have lost angles because I agree I was losing the angular dependence in there, but I don't know how to control
So do we
that
have any
angle.
numerical evidence that that is a subtle factor, that the vorticity tends to avoid being stretched after time?
For Euler, there's, well, for Euler there's a paper by Konstantin Maider and Pfefferman where they looked at angles. And the theorem is almost unusable. It's beautiful mathematics, and it takes one page to state. But, and essentially, it's all conditional. They say, well, if the angle lives in a certain cone, and the cone isn't too wide by certain then, and the omega is in LP, something or another, then you're under control. And
It may be the theorems haven't got very subtle yet.
well, you're right. That's what I'm trying to
Do we
say.
have numerical evidence that it is
Yeah.
useful to control that, because it could be quite a small term, or whether this large bound is all you need to worry about?
But from Bob's Euler calculations, you when he starts with anti-parallel vortex tubes and then they start to bend, like so, and you get the other one, you've got large curvatures around here. So the angle is important, clearly, because as you're going round the bending of this elbow, your angle in there is really going to get very strong. So if you're saying, yes, I'm losing the subtlety, the answer is yes, I am, but I have no idea if I put a mod sine or cos theta here, I wouldn't know what to do with it. That's the problem. And I'm trying to close off.
Okay, so my question was really, do we have to worry about that?
I think the answer is yes, but all what this is saying is this is just the worst it can be. And we should worry about it if our mathematics was more subtle, but it's not. No.
I think we should stop there and go to lunch. Thank you very much again, John.